So hey everyone, I'm Steven. I'm happy to close out the day. I hope everyone's not falling asleep, but hopefully we'll make it through. So my talk's called Understanding Bias in AI. Sorry. Couple of disclosures. So I'm an employee of Google. However, any views or opinions that I express are my own and not necessarily those of Google. And so to kind of open us up with a few key points, I want to make it clear that the way that we measure bias matters. There's a bunch of different ways that we could potentially define bias. There's, like handful to, even dozens of ways. And each of them really actually correspond to distinct phenomena. And, it's kind of easy to pick one arbitrarily and then come to essentially arbitrary conclusions. And so, there's a few potential implications of this. One is that we miss something important, there's some harm, and we don't catch it. Another is that we sort of design some type of mitigation or intervention that's kind of ineffective, doesn't address the problem. Another is that we, essentially do something that actually introduces harm because we measured the wrong thing and then sort of created a mitigation strategy that itself was harmful. And so I argue that, if we're sort of thinking about what we can do that's practical here, we can try to understand how really integrating rich socio-technical understandings, that's understanding about how technology interacts with society and people and technology and sort of in concert, how that can enrich our analytical approach and sort of choose the right method and way of measurement and way of thinking. And so ultimately this is a type of bridging of interdisciplinary gaps and problem understanding, and it's almost a way of making some of the things that Leo mentioned this morning concrete and things we can actually do in our analyses. I don't know I need really an introduction here, but I want to say that I'll mostly be talking about diagnostic and prognostic modeling here, kind of like classic uses of machine learning in healthcare. I'll talk a little bit about large language models, but mostly towards the end. I kind of, I think, covered what I'd like to say mostly about that in the sort of earlier topic, or the earlier panel. So there's a few different kind of objectives that have popped up in the literature and in the field when we talked about fair machine learning and bias in general. And they really are different, and I want to make that clear. So the first is kind of this focus on ensuring that we have equal performance of some kind or some other, equalizing some statistical property of a model across populations of patients. So maybe you stratify your population by age, race, or gender, or other notion of a subgroup, and you ask that the model performs equally on some basis. Another is to say that we want to understand, let's say upstream biases that affect our data and our measurement processes and the way we think about formulating problems. And this is very, very directly entangled with social and structural determinants of health that sort of affect the social patterning of the data, as Leo said earlier. And then finally, we can think about what it would mean to promote health equity in the use of machine learning and AI. That objective overlaps with these other notions, but it is actually distinct as well. And I would argue that often we are, in some sense, our end goal is this third thing, and we need to understand if that is our goal, what it is that we should measure and how that affects the way we think about design and evaluation. And so kind of along those lines, most of the time when we are doing, machine learning development and evaluation, we're kind of focused on this box, right? We have some data, we fit a model, we evaluate it on some test set that kind of, attempts to represent some prediction task or something. But that's actually quite different than thinking about this model as a part of a machine learning system. So that's, maybe some concrete policy or intervention, and that thing is a part, it's used to do something, right? And so maybe we have a predictor that predicts, the risk of a patient developing cardiovascular disease, and that would inform, who you give a cholesterol lowering medication to, right? But then if we want to talk about the, impact of that, we need to talk about who is the target population, right? Which patients do we expect to use this thing for? And what would the benefits and harms be if we were to use it in any particular way, or if the model had particular performance characteristics? Okay. And so, that what I just talked about, I think of as the downstream context, but we can also talk about this upstream context, right? And so that's kind of what I alluded to in terms of thinking about where the data comes from. And so there's a couple things I want to highlight. The first is that in most of the contexts that we're talking about bias and fairness, there are health disparities that affect the populations we're looking at. So there's kind of two distinct phenomena that are worth pointing out. that is that the distributions of the data that we have for those populations tend to be different. So we have different distributions of covariates, we have different distributions of outcomes. And the second is that the representativeness of that data is different across groups. So in particular, because we have differences, tend to have systematic differences in access to care, the extent to which the data that we have for each subgroup is sort of systematically different. We have groups that the data is more representative of than the others, even if we sort of condition on the observation of the group. Okay, and so I'm gonna start out by talking mostly within this box, saying if we've done a good job of sort of defining our machine learning problem, how can we concretely connect it to downstream context? And so actually putting aside the issues of like bias in the data, like what problems still remain, how can we use this to sort of better ground our approach to thinking about fairness and bias? And then later we'll kind of loop back to the things I just mentioned about upstream context. What people tend to do in this space is you say, okay, I have some population, I essentially stratify and ask whether performance is equal across some groups. And there's a few issues here. So as I mentioned, because we expect there to be health disparities, we do have differing data distributions across subgroups. And what's kind of a counterintuitive point is that optimal performance is not stable under distribution shift. And so what I mean by that is if I give you the best possible predictor for a data distribution, and then I look at a different data distribution, and I give you the best possible predictor in that data distribution, the performance actually tends to be different for outcomes that are sort of not possible to deterministically determine. So anytime our outcomes are noisy, this is a property we expect. And so generally, like models that are good by some notion of good in terms of they sort of lead to fair decisions, they lead to equitable policies, don't actually satisfy like notions of fairness that have become sort of commonplace. And so I'd argue that we often don't actually need equal subgroup performance. And there are actually cases where like behaving equitably or fairly actually requires us not to have equal subgroup performance. And to be clear, these are not consequences of underrepresentation in data. They sort of remain, even with arbitrarily large data sets that have been collected in a way that we might think of as being free of bias. So like, why does this happen? Because I think this is actually quite a contentious point. And so to kind of build this out, I want to give a little bit of technical detail, so bear with me. But we can talk about this, it's essentially called a score distribution. And this is basically if you have a, let's say a classifier or predictive model, you make a prediction, let's say it's a risk score between 0 and 1, you plot the distribution of that for your population. And so we can think about notions of fairness that are based on thresholding these scores. So on the left-hand side, we're looking at basically just the distributions across two subgroups, and then you can think about the area to the right of this threshold at some given threshold, and then the area to the right is basically just the fraction of the population that gets classified as positive. And we can talk about gaps between these, we can talk about gaps in this rate across groups, and that corresponds to a notion of fairness called demographic parity, which is quite common, but also doesn't really incorporate anything related to the performance of the model. It's just sort of like, basically the rate at which different groups receive an intervention. But things get a little bit more interesting when we look at actually stratifying the population based on whether the outcome is observed or not. So this is sort of an interesting thing, but when you look at the area to the right of these, the right of the threshold in these distributions, these actually correspond to notions of error rates. So if you look at the y=0 population, the area to the right is actually the false positive rate. So this is 1 minus specificity, basically. And then when you look at the y=1 population, the area to the right is the true positive rate, and this is the sensitivity or recall. And so what you see a lot of actually in this literature is reasoning about these distributions, both from an evaluation and a sort of mitigation and model design perspective, because they allow us to control notions of fairness that kind of depend on these error rates. And this notion is actually like incompatible with notions of fairness that are based on calibration. And so if you're not familiar, calibration is basically asking, if I look at any value of my score, I can basically ask, at this value of the score, what was the average outcome? And so what we might hope is that if our model is perfectly calibrated like it is for this purple group, that, let's say for patients whose risk score was 0.2, that 20% of the patients that I predicted 0.2 actually observed the outcome. And what's useful with these kind of curves is we can use them for reasoning about actually fairness in decision making. So if we look at this green curve, because the curve is below the diagonal, we're actually overestimating risk because for any given value of the score, we actually observe fewer outcomes than expected. And then conversely, on the orange curve, we're underestimating risk. So if our goal is, let's say, to intervene on patients whose risk is above 20%, we can set the threshold here, and we'll note that we sort of have different implicit thresholds of referral. So what I mean by that is that there will be patients in the orange group in particular that we would like to give the intervention to, but we are not. And then conversely, in the green group, we sort of have the opposite problem. And so, these are kind of our like classic notions of fairness. And, I think kind of just without any way to ground our problem, we don't really have any way to choose between them. And so, for example, we can look at each of these sort of separately. So, we can talk about calibration, which I also sometimes call sufficiency, but that's basically just saying that our 3 calibration curves are the same curve. And here we don't necessarily have equal score distributions, and we have different ROC curves, okay? So we have different performance under like these error rate notions. And then we talk about demographic parity. We have the same score distributions, different calibration curves, and different ROC curves. And then here we have a case that basically gives us the same ROC curve, so we sort of have the same performance, but different calibration, and these are actually slightly different score distributions. So what can we do about this? So we can actually use like decision theoretic means of evaluating our models. So in some sense, we're trying to say, we think about the model as a policy and we ask, what is the benefit that policy gives to the different populations? And so I'm not gonna go through the details of this just given time, but effectively what we can say is we want to say, like, let's get the model that actually is the best for every subgroup. And it turns out that under this notion, there is no fundamental trade-off between fairness and predictive performance. In the sense that if we look at this model that satisfies calibration, this is the optimal predictor for every subgroup. It also is the only one that allows us to pick a single threshold that is actually simultaneously optimal for every group. And so if we look at the other notions of fairness, for any threshold you pick, you actually can determine that you're picking a suboptimal one. And the only way to address that under this notion of threshold adjustment is to pick different thresholds for different groups, and that actually just corresponds to undoing the miscalibration, which actually ends up violating the notion of fairness you tried to impose in the first place. And so if we think about grounding in the context of a specific policy and its benefit, it leads us towards notions of fairness that are based on calibration and not necessarily like error rate control. Now, this is a relatively well-known phenomenon in the fairness space, but in a recent NeurIPS paper that we worked on, we actually show this is like a more general phenomenon that affects essentially all performance metrics. And so you can think about this basically saying that when we have different subgroups, there's some form of confounding. We have different distributions. The distribution of covariates, the distributions of comorbidities and so on is different. This means that because of those different distributions, we have different performance. But this is just actually like a plain notion of confounding that you might be familiar with if you've ever done work in causal inference. And so I'm not going to get into details too much, but we can use what are called directed acyclic graphs in order to specify our assumptions about the data generating process. And this allows us to make progress here. Consistent with kind of the previous talks, I argue that we can't make progress without specifying assumptions, and this provides us actually a mechanism for doing that. And so what these are basically is we can write out the different variables that we're interested in. So when we talk about X, for example, we're talking about the features that we're using for prediction typically, and then Y refers to outcomes. And in this graph, this means that essentially these covariates are the causes of Y, and then we can talk about some notion of a subgroup A. And here, what's particularly important is that I don't think of A as being a cause of anything. So if we're talking about race, as we often do in fairness contexts, you can think of this as a context where there's sort of differential exposure to social and structural determinants of health that mean that there's some unobserved confounders that are different in distribution across subgroups. And so when we look at this graph, that is the case. However, it turns out that because all of this effect is sort of blocked by this variable here, it turns out that this corresponds to an assumption that the relationship between X and Y is the same across all groups, even if we're assuming that this distribution is different. So, however, in this other graph, we have this, this arrow here, which basically means that there's some effect that is not explained by this variable. So for example, if we're making predictions of some future health outcome, we could measure we could measure the patient history at some time, and if we have some group that receives systematically poor healthcare kind of after that measurement point, their outcomes will be worse even given the same baseline covariates. And that's sort of represented by this here. Now, the interesting thing is this actually gives us the ability to understand why our models behave the way they do. So under that graph on the left, because we sort of assumed that the relationship between X and Y is the same across groups, in some sense, the subgroup agnostic predictors, that's the one that's just based on these covariates, does generalize in some sense across the groups. However, it doesn't actually achieve equal performance necessarily. Now, it's also calibrated for every subgroup. However, if we talk about this model, that one, actually, we expect that it, in some sense, doesn't generalize. There's a different statistical relationship. Relationship between our outcomes and our covariates across subgroups. And if we're just looking at performance metrics and calibration, it actually implies that, in some sense, fitting a different model for different groups improves performance for the subgroups. And you can kind of extend this in a bunch of ways and talk about different sets of assumptions. I'm not going to go into details, but I'll just point out that this set of graphs here, which we call sort of the anti-causal direction, these are ones where you think of the outcome as actually being upstream of the covariates. This is more typical for things like diagnostics from chest x-rays, where in some sense, there is some set of conditions, let's say pneumonia, and you think of there being a particular presentation associated with that condition. And what's important is that actually all of these graphs, except for the covariate shift graph, have the property that you expect subgroup-specific prediction to improve performance. And so this exposes a particular sort of conceptual conflict in the sense that if we're evaluating models in terms of performance, and we also sort of disagree with the notion that we should be using subgroups in those predictions, we have a conflict in the sense that under all of these reasonable graphs, it actually turns out that subgroup information does improve performance. And you can understand why performance differs in the general case across subgroups by considering basically the fact that performance metrics are nothing more than functions that depend on variables in these graphs. And we can sort of ask the question, under these graphs, do we expect the distribution of predictions and outcomes to be the same across subgroups, which sort of serves as a sufficient condition of equal performance. And it turns out that this is never the case in any of these graphs. And so it's not to say that predictive performance can't be equal, but that we in general don't expect it to. However, we can actually talk about in these different graphs, why performance is different in terms of thinking about control. So here, in this covariate shift graph, if you think about a predictor that only depends on X on our covariates, basically there's a predictor node that points out of X, and then Y also points out of X. And so for any given value of covariates, we have the same distribution of predictions and outcomes. And so any difference in performance across subgroups is actually explained by this change in the marginal of X. And so there's many other examples of that, in the label shift case, Y sort of serves as that sufficient conditioning variable. But in general, this allows us to understand why performance is different on the basis of the data generating process. We also have a method for doing confounding control in evaluations that looks a little bit like propensity score reweighting, but I'm not going to get too into that. So we can look at what happens under all of these different, basically all of these different cases, and look at things like calibration. And so on the top, we're fitting a model that only has access to covariates. And what you see basically is that under the covariate shift case, you have calibration for both groups, sort of as we expect, because the ground truth is invariant across groups. And that doesn't happen in any other case except this case that I'm calling separable. And what this is actually similar to the case that Judy mentioned earlier, which is that we have basically data that fully encodes the subgroup. And so, for example, if it's possible to predict the subgroup with perfect accuracy, it doesn't matter what the causal graph is. We sort of get this property where the model, in some sense, latches onto that information. And then, as you can see, when you fit the model with subgroup membership information, you kind of get this calibration no matter what as well. And then we can also verify the property with respect to improvements in performance, sort of with subgroup membership information in the predictor. And basically what this shows is that in this set of cases I outlined, like you can show that performance does improve, but kind of importantly, the sensitivity and specificity results are sort of all over the map. And this is actually completely expected and part of the reason why I'm arguing that those types of evaluations are somewhat misleading. However, if you sort of look at this net benefit metric that I alluded to earlier, you sort of get a consistent reweighting of those, or rather you get a particular reweighting such that you still see these kind of like monotonic improvements. The controlled evaluation procedure behaves like we expect it to. Okay, so, and I want to shift gears a bit. I've been mostly talking about the case where we sort of assume that we have data that's been collected without bias, and I want to sort of move on to challenge that assumption now. So I'll primarily focus on sort of selection bias, so we'll formalize this notion of sample selection bias that Leo mentioned, and we'll also talk about the sort of the problem that Judy mentioned, which is related to proxy variable selection. And so there's a few things that are sort of common to the setting, and that is that these types of biases cause our data to be differentially misrepresentative. I mentioned that earlier. Our data is misrepresentative in different ways for different subgroups, and what this means is that there's no way to look at your data on its own and determine whether it sort of satisfies your fairness criteria. And so we need some form of causal knowledge that we specify to allow us to link the observed data sort of to like the unbiased real world. And I think in general, despite there being broad awareness that data biases are important, there's actually relatively few analytic tools for understanding them that are like well known in the machine learning community, and it's an entirely distinct thing from thinking about the set of fairness metrics and disaggregated performance evaluations. But it turns out we can actually do a lot, basically just by augmenting our causal graphs with a notion of like a selection node. And so what this means is if we're willing to make assumptions about the set of variables that affect the process by which data enters into our sample, we can come up with a rigorous and principled approach for correcting either the model fitting or the evaluation procedure. And again, I'm not gonna get into details, but we basically have fully characterized what happens under different assumptions on selection bias. Okay, so I want to talk a little bit about now biased proxy labels. So this is the basically the problem that you don't observe the outcome you wish you observed, so you pick another one, and the relationship between that proxy label and the thing you wish you measured is different for different groups. And this has the same set of issues I mentioned before, but here we tend to see that if you, in some sense, fit the best model you have to your biased proxy label, you'll have differential miscalibration across subgroups with respect to the true label of interest. And so this has that fairness masking property. And so the most famous example of this is the one that Judy actually showed. And so here, this is the case where you are, in some sense, fitting a model to predict healthcare expenditures on the assumption that that is a good representation of healthcare needs. And so the problem is that there's systematically different access to healthcare across groups in the United States. And if you have poor access to healthcare, the quality of this proxy will be systematically lower. So if we're given level of healthcare needs, you'll have fewer recorded historical expenditures. And so what this means is if you do a good job of predicting cost, you sort of actually induce a fairness gap with respect to the label, or rather with respect to another proxy label that you believe is unbiased with respect to your true construct of interest. And as you'll notice, these are essentially calibration curves and correspond to that notion of fairness in decision-making that I mentioned at the beginning of the talk. And so we've actually also kind of incorporated this into our sort of causal graph way of thinking, and you can essentially model the unbiased proxy case as this world where you think about your, in some sense, your observed outcome. Let's say here that's this notion of number of comorbidities as being, directly related to your true label of interest. But then in the world where we have a biased proxy, there's essentially some confounder that kind of goes around our true outcome. And so what that means is that the relationship between the true label and the proxy label is different across the groups. Even if we fit a good model to the observed label, we have done a bad job of fitting sort of the true label, and the extent of the error is systematically different across the groups. And so we actually replicated the original Obermeyer study using the data they released, and there's a couple interesting things that come out, which is that if you look at their original data, you actually see there is a little bit of a gap when you plot it this way, or at least in our replication, and you can mitigate that by fitting a subgroup-specific model. Now, obviously, this is a problem because we know this is a biased label. So what we find is that if you in some sense, fit subgroup-dependent models to biased data, you actually, kind of as you'd expect, make the bias worse with respect to your true label. And so this maybe gives us some ability to talk about when it may make sense to, fit subgroup-dependent models on the basis of whether we believe our outcomes satisfy this biasness property. Okay, so to close this out, I wanted to talk a little bit about LLMs, and I think we preempted a lot of this conversation in the earlier panel, but I think the main point I want to convey is that really a lot has changed in the last few years in terms of the way people are thinking about specifying their problems and how they think about evaluation, and a lot of that has to do with the way that LLMs sort of work, but I don't think this is a fundamental gap. And so, but the basic problem is that in some sense, the input encodes the user intent, the use case, and the context. So this means that in some sense, the task is variable, right? We can't specify a single task. It, in some sense, changes on the fly, and it changes per query, and it's kind of loosely specified. So we don't actually know what the user wants in all cases, nor how to evaluate it. And kind of as we discussed earlier, there's sort of a need to evaluate these multidimensional complex properties of these outputs using things like human rating processes. You can talk about these model-based evaluations. So, it's either asking an LLM directly how you should rate, perhaps you give it the rubric, but you can also talk about kind of fitting models to ratings data and using that as a predictor. And that still has problems, but maybe is better than kind of the zero-shot prompting approach. And then another thing I want to mention is that everything I was mentioning before, or sort of in the context of classic ML, requires this notion of a target context, specific, intended use and target population. The way people have constructed evaluations of LLMs so far has largely kind of focused on, let's say arbitrary distributions of data. You have some benchmark, it's some set of queries, and there's no real correspondence between the distribution of those things and perhaps the distribution that you care about in the real world. So there's maybe some question about whether or which conclusions are valid on the basis of those evaluations. And to be fair, some of those evaluations are, particularly trying to probe at failure modes rather than, let's say measure performance in a deployment context, but it's important not to conflate these things. And so there's a lot more to say about that in the context of quantifying bias, but if you're interested in that, you can talk to me or check out this paper that was in Nature Medicine about a year ago, and Leo's there as well somewhere. Here you go. Okay, so I hope I've convinced you that the evaluation of simple models is highly nuanced and not as easy as maybe you would have assumed. But overall, I think we can make progress if we're willing to evaluate the impact of systems in the context in which they're intended to be used, and by integrating, let's say rich socio-technical understanding in a very interdisciplinary way, and sort of by committing seriously to bringing in more rigor and formality to the way we think about encoding those types of assumptions. And furthermore, I want to caveat all of this by saying that pretty much everything I've talked about today is really within this narrow lens where we sort of assume that all the levers we have to pull are something that is sort of imposed on the machine learning model. But if we are truly interested in addressing upstream structural causes of inequity, perhaps we could think about other interventions that don't look like anything we talked about today, and perhaps more directly address the upstream causes and so on. So with that, I will end, and feel free to send me an email.